Hey, welcome back. Every chemical reaction tells a story. We see the beginning, the reactants, and we see the end, the products. But just like any really good story, the most interesting parts are usually hidden somewhere in the middle. Today, we're going to pull back the curtain and uncover one of those hidden plots. Just think about that for a second. What if all the main characters are right there on stage, but some secret, off-screen player is the one really pulling the strings, deciding how fast the whole story unfolds? Well, that's exactly the mystery we're diving into today. All right, so here's our case. We've got hypochlorite reacting with iodide to form hypoiodide and chloride. I mean, it looks simple enough, right? Pretty straightforward, seems like it should be a one-step story. But as we're about to find out, looks can be very deceiving. And here it is, our first major clue, the hydroxide ion. Now, you can look all you want, but you won't find it in that final balanced equation. And yet, it's secretly involved in how this reaction actually goes down. It's a key player, not just some random bystander. So, to figure out what's really happening, we have to look past that overall equation and go backstage right into the reaction mechanism itself. This is where we uncover the secret steps of the story. And here's the real story. This reaction doesn't just happen all at once. It's more like a three-act play. First, you've got a really fast setup. Then comes this slow, deliberate second step. And finally, a super quick conclusion. And hey, look who's making an appearance in steps 1 and 3, our hidden character hydroxide. This mechanism also introduces us to a couple of new characters, HOCl and HOI. We call these reaction intermediates. Think of them like temporary props in our play. They get created in one scene and then completely used up in the next. And because they're so fleeting, trying to measure their concentration is incredibly difficult. Keep that in mind, because it's going to be really important in a minute. You see, in pretty much any multi-step process, whether it's an assembly line in a factory or a chemical reaction, there's always one step that's way slower than all the others. This step is the bottleneck, and it basically controls the overall speed of the whole operation. So, let's find ours. That second step, yep, the slow one, that's our bottleneck. It's what we call the rate-determining step. And what that means is that the speed of the entire reaction really only depends on the reactants in this one specific step. That's the iodide and our intermediate, HOCl. And, here's our big problem. We have this perfect-looking rate law, but it contains a term for HOCl, one of those super fleeting intermediates that we can't practically measure. It's like trying to solve a mystery when your most important piece of evidence just keeps disappearing. So what do we do now? Well, we put on our detective hats and do some chemical investigation. We're going to use what we know about the other steps in the mechanism to figure out a way to write our rate law using only the stuff we can actually measure in a lab. Let's circle back to step 1. The fact that it's a fast equilibrium is a huge clue for us. All it means is that the forward reaction and the reverse reaction are happening at the exact same speed. They're in perfect balance. So mathematically, we can just say the rate going forward equals the rate going in reverse. Now, since those two rates are equal, we can do a little bit of simple algebra and just rearrange that equation. We can solve it for the one thing we're trying to get rid of, the concentration of our elusive intermediate, HOCl. And just like that, we've defined it using things we can measure, hypochlorite and our mystery guest, hydroxide. Okay, this is the moment of truth. We're going to take this new expression we just found for HOCl, and we're going to plug it right back into the rate law from our slow step. We're replacing the thing we can't measure with things we can. And there it is. This is the true rate law for the overall reaction. And just look at what's in it. Our original reactants, iodide and hypochlorite, and right there, sitting in the denominator, is our hidden character, hydroxide. All right, we've done the detective work, we've cracked the code and found the true rate law. Now it's time to deliver the verdict. What does this equation actually tell us about what the hydroxide ion is doing? It's all about location, location, location. The concentrations of our reactants, iodide and hypochlorite, they're up top in the numerator. That means if you increase them, the rate goes up. Simple enough. But the concentration of hydroxide is in the denominator. So what happens if you increase its concentration? The overall rate actually goes down. So, mystery solved. Hydroxide isn't a catalyst helping things along, it's the total opposite. It's an inhibitor. It's that secret character that was slowing down the whole story from behind the scenes. The more hydroxide you have, the more it pushes that fast equilibrium in step 1 back to the left, which means there's less of that crucial HOCl intermediate available for the slow step. And this isn't just a cool theory, it's backed up by real experimental data. When you actually plug in the measured concentrations and the reaction rate, you can calculate this effective rate constant, which basically bundles up all those individual K values, and it comes out to 3 inverse seconds, the real-world proof of the mechanism we just uncovered. It really makes you wonder, doesn't it? I mean, we see reactions happening everywhere, from massive industrial processes to the biology inside our own cells. What other invisible inhibitors are out there, quietly controlling the pace of the world, just waiting for us to discover them? Definitely something to think about. Thanks for joining me.